Right, so here we go, 9FMO, 2022 paper, to the 3 seats. Question 4 on the oblique collisions. So we've got 2 uniform spheres, A and B, equal radii. The mass of A is 3m, so it's 4m, moving a smooth horizontal plane. So if you like, this diagram is looking from above, and they collide obliquely, so they sort of hit each other like this. And equal the collide. A's moving speed 3u, 30 degrees to the line of centres. B moving speed 2u, the line of centres. And just B's moved through an angle of 90 degrees by the collision as shown. So it's going up to the left, and then it's going up to the right. But it's turned through an angle of 90 degrees. And we've got to find the angle which A turns through and the impulse. Now, remember, I can split the velocities of A and B into 2 components: parallel to the line of centres, and perpendicular. The one that's parallel, I've got to multiply by cos 30 because that's the angle I've got to turn it through. I could write that as u times 1.5 root 3, but I'm not really keen on that, to be honest. The one that's perpendicular to the line of centre, I've got to turn through an angle of 60 degrees. So it's 3u cos 60 or 1.5u, which I don't mind. And then for B, along the line of centres, it's going to be 2u cos 30 or u root 3, which is almost all right. And then the one that's perpendicular to the line of centres is going to be 2u cos 60. Cos 60 is a half, so that's u. That's nice and tidy. I'm going to stick with that. I'm not keen on the root 3 bits though, so I'm going to stick with the 3u cos 30 as the number I'm going to use. Now, after the collision, the component perpendicular to the line of centre stays the same, so that's still going to be u. And we're going to find out what this v is, the component parallel to the line of centres. For A, that 1.5u stays the same because it's a smooth collision. They're not dragging each other up or down. It's nice and smooth when they hit each other. The only change in their velocities is the component parallel to the line of centres. And then after the collision, A's got a component parallel to the line of centres. I'm going to call that W. It's going up to the left. Now, because it tells me the angle that B turned through, I can draw the velocity of B like this, and I know that those components are V and U, and that angle's 60 degrees. So I can write the V in terms of U now. Tan 60 is U over V. So the V is going to be equal to U over tan 60 or U over root 3. And the only component that I don't know now in terms of U is that W. I'm going to find that with the momentum equation. The angle we're trying to find, though, if I continue the original path of A down to its new one, that's the angle we're trying to find. That's the angle it's deflected through. Now, the momentum equation looks like this. There's no mention of restitution anywhere in this equation, no elasticity, so it's just the momentum I'm going to use. Before the collision, the A's got a component along the line of centre of 3u cos 30. So 3mu times 3u cos 30, that's in the positive direction. The B, that's going in the negative direction, and it's got a mass of 4m, a component of 2u cos 30, so minus 4m times 2u cos 30. Then after the collision, A's going in the negative direction, parallel line of centres, so minus 3m times w. B's going in the positive direction, so it's 4m times v. I'm going to solve that. I'll get rid of the m's first. The left-hand side actually is 9u cos 30 minus 8u cos 30, so it's just u cos 30 on the left-hand side. I'm going to say w equals, so I'll take the minus 3w over and the u cos 30 over. So that'll be minus u cos 30 on the right-hand side, or minus u times root 3 over 2. And then I've got plus 4v, or plus 4 times u over root 3. I need to add minus root 3 over 2 and 4 over root 3. As further mathematicians should be able to do that in your head, really. 5 root 3 over 6. Common denominator 2 root 3. The top line is going to be 4 times 2. Take away root 3 times root 3. 8 take away 3 is 5. 8, so it's 5 over 2 root 3, or 5 root 3 over 6. Divide that by 3 to get W, 5 root 3 over 18. Now, I'm going to find that angle first. I'm going to call it theta. Here's the velocity of A after the collision. I know that the components are 1.5 u in that sort of perpendicular to the line of centre's direction, and that W, 5 root 3 over 18 u. So the tan of that theta is going to be 1.5 u divided by W. If you can stick that in your calculator, it's 1.5 times 18 over 5 root 3, which simplifies to 9 root 3 over 5, giving an angle of 72.2. The angle we want, though, is 180 minus that and the 30, which gives us an angle of 77.8. There we go. And then the second part, the impulse, well, remember, it just acts along the line of centres, call it I, mass times the change in velocity. The final velocity is that V, that's in the positive direction, because it's going to the right, and then minus the original velocity before the collision, which is minus u root 3, so it's minus u root 3. So you've got to add 1 over root 3 and root 3, which is actually 4 root 3 over 3, and you end up with 60 root 3 over 3 times mu, and there you go.